In this lecture, we are going to be looking at the practical exam questions for medicinal chemistry, which is PCH 422, the second semester medicinal chemistry 2. And we are going to look at the previous exam questions, that is the questions they set in the previous exams, and also some forecast questions, that is some questions we should be expecting based on what we have done during the practical session. Now, for the past question, I have one of these past question here. It says define the following parameters and state their respective formula. The acid value. Now, so I'm going to define it. If you want to write it down, you can write it down, but I'm going to explain it. Now, whenever you hear of this acid value, what is it actually talking about? The acid value is a measure of the amount of free fatty acid present in a substance. The amount of what? Free fatty acid. Because when you are talking about the acid value, most times what you are actually looking at for is organic acids and not just mineral acids. Now, the amount of free fatty acid present in a substance. Now, how do you actually determine this acid value? Is by acid-base titration. How do you determine the acid value? Is by what? Acid-base titration. Now, we said acid-base titration is used for standardization and the assay of either an acid or a base. It is used for standardization and the assay of either an acid or a base. So if you want to determine the amount of acid present in a substance, you use a base to quantify it. Is that understood? If I want to determine the amount of acid present, what do I use? I use a base to quantify it. However, if I want to determine the amount of acid present in a substance, a base present in a substance, I use an acid to quantify it. That's why they call it the acid-base titration. So we said the acid value is a measure of the amount of free fatty acid present in a substance, and it is typically expressed as a number of milligram of KOH, the number of milligram of KOH or sodium hydroxide, the number of milligram of KOH or sodium hydroxide, KOH potassium hydroxide or sodium hydroxide that is required to neutralize the free acid in 1 gram of the substance. That is required to neutralize the free acid in 1 gram of the substance. That is the acid value. Is that okay? Can I say it again? That the acid value is a measure of the amount of free acid or free fatty acid present in a substance. And how do you quantify it? I told you that if you want to quantify an acid, use a base to quantify it. So we actually use this base here, either KOH or sodium hydroxide, to quantify it by acid-base titration. How is it expressed? We say it is usually expressed as milligram of KOH or sodium hydroxide that is required to neutralize 1 gram of a substance. That is required to neutralize 1 gram of what? Of a substance. Are you getting it now? Or that is required to neutralize the free fatty acids that are present in 1 gram of a substance. So if you have 1 gram of, let's say, a particular substance, and of course that substance contains free fatty acid, you want to know the amount of free fatty acid that is present in this 1 gram of this substance. What do? You titrate it with either KOH or sodium hydroxide. Now, the amount of KOH or sodium hydroxide that neutralizes 1 gram is what is called the acid value, expressed in milligram per gram. All right, expressed in milligram per gram. Is that okay? That is milligram per 1 gram of the substance. It is commonly used in the analysis of fat and oil and determination of their quality. The acid value is used for the analysis of fat and oils, and also for the determination of their quality, their freshness, and their degree of rancidity. Now, a higher value indicates a high value of free fatty acid, which can be an indicator of spoilage or poor quality of fat or oil. So high acid value means high free fatty acid, and high free fatty acid means that the oil or fat is not good or it's getting bad. So that is the acid value. Now, what is the formula for calculating acid value? represented with A, V, acid value, is equals to A minus B. Now you must state your parameter times molarity times 5.56.1 divided by the molecular weight, where A minus B, they are volume, so you can say VA minus VB. Volume of what? The volume of either KOH or sodium hydroxide used. Is that okay? KOH or sodium hydroxide used. While M is the molarity of either KOH or sodium hydroxide used. And then 56.1 is the molar mass of KOH, in this case potassium hydroxide. Are you getting it now? So if you use sodium hydroxide, this 56.1 will be now be the molar mass of sodium hydroxide, of course, which is equals to how many? 40. Do you understand? But this formula is for what? The KOH, which is the molecular mass of KOH. Is that okay? If you calculate, potassium is 39 point, I think, 1, oxygen is 16, hydrogen is 1. All right. Now when you add this plus this, it's going to give us 56.1 gram per mole potassium hydroxide. So this 56.1 is the amount in gram of sodium hydroxide, and then W is the molecular mass, the mass of the sample used. That is the mass of the substance that is used. Are you getting it? Is the W. So VA minus VB, VA and VB is the amount of titrant. In this case, the titrant that was used for this experiment is potassium hydroxide. So this is how to calculate the acid value. All right, it's based off on acid-base titration to give us what? Salt plus water. Is that okay? So that is for the first one. Let's see for the second one, the saponification value. Now the saponification value is still almost the same thing as the acid value, but saponification is a reaction that involves a fatty acid and sodium hydroxide or potassium hydroxide. I think the one we are going to use is potassium hydroxide to give us something like this or something like this. All right, the ester. Now this is a saponified product, and this is actually used for making of several soaps and several other substances. Now saponification value, how is it defined as? It's defined as the measure of the amount of alkaline. You see that it actually is a reaction between an acid and a base, right? You want to know the amount of alkaline, in this case required to saponify a certain amount of fat. The amount of alkaline required to saponify a certain amount of what? Fatty acid or fat and oil. It is expressed as the amount of KOH required to saponify 1 gram of the substance. So you see that it's almost the same thing like the acid value, but this time now you are talking about saponification. The amount of KOH expressed in what? Expressed in milligram, that is required to saponify 1 gram of either a fat or what? Oil. That is the saponification value. Now listen, the saponification value also has formula almost. Now for the this same value, for the acid value, use normality, not molarity. So the formula for that acid value is supposed to be, sorry about that, 56. I said VA minus VB times normality times 56.1 divided by W. So in place of this normality, in place of the molarity that I wrote before, please correct it to normality. Is that okay? Why for saponification value, the formula for saponification value is SV saponification value is equals to VA minus VB times 56.1, that's molarity, divided by W, where W is, of course, the mass of the substance. VA minus VB is the amount of acid. There's a particular acid that was used for the titration. We can say the amount of KOH, and then 56.1 is the molar mass of KOH, and then M is the molarity of KOH that was actually used for the titration. It's almost like the acid value. The unit is in milligram, so any value you get is in milligram. All right, that is that for saponification value. So saponification value and acid values are almost like the same. Now, the next one is the iodine value. Now, iodine value is used to actually look at the saturation, or the degree of unsaturation, the degree of unsaturation of an organic compound. Are you getting it now? It is used to determine the degree of unsaturation of an organic compound. It is expressed as the number of grams of iodine that can be absorbed by 100 grams of the substance. It is expressed as the number of grams of iodine or iodine that can be absorbed by 100 grams of the substance. Just know that the iodine value is used to determine the amount of unsaturation in a substance, particularly in fat and oil. It is expressed as the number of grams of iodine that can be absorbed by 100 grams of the substance. So if you have 100 grams of the free fatty acid, now you now start supplying it with iodine. The amount of iodine in gram that can be absorbed by 100 grams of the fatty acid is what is called the iodine value. And for this fatty acid to absorb iodine, it means that the fatty acid must be what? Unsaturated. It must be what? Unsaturated. So that's the iodine value. Now, what is the iodine value? The formula. You use the formula. Iodine value is equals to B minus X times normality times 12.69 divided by the molecular weight of the compound. B minus S is the volume of sodium thiosulfate used, because this practical will actually require the use of sodium thiosulfate, which is something like this. All right, so the B minus S is the volume of sodium thiosulfate used, N is the normality of the sodium thiosulfate used, and W is the molecular weight or the molecular mass of the fatty acid used, or of the sample. The molecular mass, the mass of the sample used, not molecular mass. The mass of the sample used is our W. All right, there's this 12.69 is a conversion factor. The molecular mass of iodine is 126.9, but after calculation we arrive at this 12.69 as a conversion factor. B minus S is the volume of sodium thiosulfate, because sodium thiosulfate is what is actually used for the assay of what? Iodine in iodometry, if you can still remember that practical we did. All right, so that is that for the iodine value. Now, the Ester value. Ester value is, how do you form ester? Ester is a reaction between an acid and a base. So ester value is just like the acid value also. Is the amount of sodium hydroxide or a base that is required to esterify 1 gram of an acid. Are you getting it now? Now, the formula for calculating ester value is equals to saponification value minus acid value. So saponification value minus acid value will give us the what? The ester value. Is that okay? Saponification value minus the acid value will give us the ester value. So that is basically how to go about this question. Now, what is thin layer chromatography? I believe this is not something that is new to us. Now, a thin layer chromatography is a chromatographic technique that is used for the separation of compounds into different components, right? Into different components. It works on the principle of what? Partitioning. Now, it contains a stationary phase and what? A mobile phase. Now, the stationary phase required a plastic, a glass, or paper that has been impregnated with substances such as alumina or silica. While the mobile phase is a mixture of solvents like hexane and ethyl acetate, ethanol and water, methanol and water, chloroform and methanol. It's a mixture of solvent. Are you getting it now? Now, you can explain the process of thin layer chromatography. It's not something that is. This is the developing chamber where you pour your solvent system in it, allow it to develop, and then you put your paper just a little bit. Shouldn't touch the line. There's a line that is written here where you spot. All right, you spot your compounds somewhere around here, and then what happens is this water move up the paper by means of capillary action, right? And as it moves up the paper by means of capillary action, the substitute the spotted this thing will start moving along based on their attraction or their affinity with the mobile or the stationary phase, and they will be separated. Like you may have a red color, then you may have another one that is blue somewhere around here, and then you may have another one that is green somewhere around here, and then you may have another one that is purple somewhere around here. Then you calculate the RF value. All right, so that is thin layer chromatography, something that all of us we already have an idea of before now. Is that okay? Now list 3 stationary phase and 3 mobile. This is not member, this mobile phase used in TLC experiment. Now the stationary phase, we are going to go with the stationary phase first. What are the stationary phase used in TLC, my dear student? You have 1, silica gel, 2, alumina. Alumina is also aluminium oxide. 3, you have cellulose. All these are stationary phase. Now the next one is the mobile phase used in TLC. Now the mobile phase are, you have a mixture of hexane and ethyl acetate. This mixture will be good for non-polar. Are you getting? This is a non-polar phase because of hexane present there, and also ethyl acetate, not that polar. Then you also have a mixture of ethanol and water. It can be methanol and water, it can be ethanol and water. Then you also have a mixture of chloroform and methanol. All right, all these ones, they are the mobile phase and the stationary phase that are used in thin layer chromatography. All right, and I believe that is the answer to that question. All right, let's look at the C. Mention 5 stains or method used for revealing compounds in TLC. 5 stains or method used. Now, UV absorption by using the UV lamp. You can use the UV absorption by using the UV lamp to show black spots to show dark spots for compounds. And then iodine vapor staining. Iodine vapor staining. These are methods. Then 3, you can use anisaldehyde, anisaldehyde staining. Then the 4th one is anhydrine staining. This one will give up purple spots. And then the last one would be, where's the last one? Potassium permanganate staining. Potassium permanganate staining. Now this potassium permanganate staining is for unsaturated compound. All right, so these are the various staining techniques that have been used in layer chromatography. Arrange the following solvent in either ascending or descending order of their polarity. Now, one thing that you should know is that for ethanol, the longer the chain is, the lower the polarity. All right, and also polarity is definitely based on the electronegativity, the electronegativity of the atoms, the arrangement of the atoms in space. All right, that is what actually informs polarity. So if you want to base on that, of course, N-hexane is the least polar here. N-hexane is the least polar. It is less than. Now between chloroform and dichloromethane, which do you think is less polar? Chloroform is less polar than dichloromethane. Alright? Exactly. Chloroform is less polar than dichloromethane. Now, after chloroform, the next one that you should follow is either methanol, ethanol, or water. Water is the more polar of everything you have listed here. Water is more polar than everything. So we are not talking about water now. Either between methanol and ethanol, I told you that the longer the chain, the less the polarity. So ethanol is less polar than methanol. Then less than water. Water is the least polar of every compound you have here. I mean, it's the more polar. And N-hexane is, of course, a non-polar compound. All right. Now, complete the following reaction involved in the bromometric determination of phenol. Now, in the bromometric determination of phenol, you have something like this. B arrow, like we said, potassium bromine plus B arrow, potassium bromate, then potassium bromine plus 6 molecules of hydrogen ion. So this one will give us 3BrO2 plus H2O. Alright, now you now have this phenol here. It's for the assay of phenol. Then OH. Then 3BrO2. Now, this is where they put the comma on. So what they expect you to put here is 3BrO2. And then this is going to give us, it's more like a bromination reaction. Now, because of this OH here, bromination can either take place at the auto position or the para. So, because OH is an auto para director. OH is what director? Auto para director. So, we are going to have bromine here, bromine here, bromine here, which will give us tribromophenol plus 3 molecules of what? Hydrogen bromide. So this is what is expected from you in this particular one. It's very easy, right? Now let's see the next question. How would you prepare 1 molar HCl in a 50 ml volumetric flask from 100 ml of 2 molar HCl acid? Now you might be tempted to use the formula C1 V1 equals to C2 V2. Yes, you might be tempted to say C2 is 100 ml, V2 is 2 molar. If you do this, you'll be in mess because this one they already gave you 1 ml of this. So you want to prepare this. So let us say our C1 is the concentration 1 molar HCl. V1 is 50 ml HCl. Now this is what you want to prepare, but they gave you 100 ml of 2 mol HCl. Now you want to know the amount of this 2 molar HCl you are going to take. So your V2 is unknown. All right, that is one thing that I was trying to say, that if you say this C2 is 100 ml and V2 is 100 ml and C2 is 2 molar, you'll be wrong. V2 is unknown because they gave you the 100 ml does not mean you are using the entire 100 ml. It means you have to take a portion from the 100 ml. So we want to know how much you are going to take from this 100 ml that will give us our desired concentration here, which is 1 molar HCl. So V2 is unknown. However, C2 is giving us 2 molar. So plug in this into this equation. If you plug in this into this equation, you are going to have 1 times 50 is equals to 2 times V2. All right, we are talking about volume here. So this becomes 50 is 2 V2. Divide both sides by 2. And then what you are going to have here will be V2 is equals to 25 ml. So what this means is in 50 ml volumetric flask, you take the 50 ml volumetric flask. I'm going to write all this. Then measure 25 ml of 2 molar HCl. All right, measure 25 ml of 2 molar HCl. Let's say this is the mark. You put the 25 ml here of 2 molar HCl, and then you add water up to 50 ml. You prepare 1 molar HCl in 50 ml volumetric flask. So that's basically what to do. I think there was one other question we didn't write. We didn't write one question. Let me write it here. Describe how you prepare 1 molar HCl from concentrated HCl acid. 1 molar HCl from concentrated HCl acid. Now they say describe. So what you first of all do is you should take precaution that concentrated HCl acid is very, very concentrated, and hence you should be very careful. You should take it to fume cupboard for your experimentation. For your if you want to collect the 1 molar HCl, you take the concentrated HCl, you should take it to fume cupboard so that you will not mess up the entire lab with the fumes from HCl. Now, having collected that, what you need now is to calculate or note the concentration. You are just writing this. Note the concentration of HCl given. So you note the concentration. All right. Now, having noted the concentration, now you are now going to calculate the volume of the conc HCl that will be required to give 1 molar in 1000 milliliter volumetric flask using the formula C1V1 equals to C2V2. How will we determine that? Get the volume and put it in the calculated volume and put it in the 1000 ml volumetric flask, and then top it up with water. By so doing, you prepare 1 molar HCl. All right. Now,